Hello, Chem 2. Today we're going to show you some aqueous stoichiometry hacks, situations where you can actually use some equations in order to make some of the calculations quite a bit easier. It doesn't work all the time, but it should work for special, unique circumstances. The first one that we're going to do is called the dilution equation. A dilution is a very, very typical, very simple type of aqueous situation where you're going to take a higher concentration of sample and you're going to dilute it down to a lower concentration. Take a small amount of the high concentration material and add a bunch of water to it in order to make it more diluted. Typical equation looks like this, where it says molarity of the stock times the volume of the stock equals molarity of the dilution times the volume of the dilution. Essentially, since you know that M and V, M times V, molarity times volume is equal to moles, you're saying whatever moles you take out of the stock, you're going to put in the dilution. You're making the two sides equal. Let's look at one of two typical examples. In a dilution, you're going to take some sample. Notice here you have this amount of material that's you're pulling out of this dark solution. This is a dark blue solution. You're pulling some set amount out and you're putting it over into another container. And then once you transfer it over to the new container, you're going to bring it up to water, bring it up to volume with water. And now this stuff is going to be more dilute, less concentrated than your original sample. That's how you make a dilution. Let's look at an example. First example is we're going to try to figure out what the concentration is of the solution you make. So here's the example. It says, what is the concentration of a solution that is made by adding 25 milliliters of a 0.45 molar solution to enough water to make 750 milliliters of the solution? Notice it did not say that we were going to add 725 milliliters to the 25. The volumes are not always going to be additive. In this situation, being very specific, adding enough water to make 750 mils. So what we're going to do is we're going to use the dilution equation. M times V equals M times V. We're trying to solve for the molarity or the concentration of the dilution. So we're going to manipulate this equation in such a way to make it equal to M dilution. M stock, V stock, divided by V dilution, essentially dividing both sides of the equation by the volume of the dilution. Put our numbers in, and since our concentration of our stock was 0.45, our volume we took out was 25 mils. We put it into 750 milliliters total. We get a new concentration of 0.015, quite a bit lower than the 0.45. Well, that makes sense. We're taking only 25 mils and adding a whole lot of water to it to bring it up to the 750 milliliters of water. That's example number one, where you're able to find the concentration of a solution that has been made if you know how much you're adding and what the total volume is. Okay, our second example is one where we're going to try to figure out the volume of our 2 molar solution that we need to use in order to make a solution. So we know we want to make a very large amount, 1.7 liters or 1,700 milliliters of a 0.05 molar solution, a pretty low concentration. And all I have in the back is I have 2 molar solution that I can make it from. I'm asking how much of this 2 molar solution do I need to grab and put it into a container and fill it up to 1.7 liters or 1,700 milliliters and ultimately end up with a 0.055 molar solution. So I'm going to use the dilution equation, but this time I'm solving for the V stock. So I'm going to manipulate this equation, divide both sides by molarity of the stock, and then plug in my numbers. So I know that I want to make a concentration of 0.055. I want to make 1.7 liters or 1,700 milliliters. And I want to, as the solution I have, the stock that I have is 2 molar. I do the math and I find out that if I grab 47 milliliters of my 2 molar solution, 47 mils of my 2 molar solution, put it into a container, dilute it down to 1.7 liters or 1,700 milliliters, my resulting solution is going to be 0.055 molar. The other application that is I what I call an aqueous stoichiometry hack, is the titration equation. Now, almost all the titrations, except for the KHP that you guys did on Thursday and Friday, were the same type, where you were titrating a solution, an aqueous solution, with another aqueous solution. Most of the time, you were taking a titrant of sodium hydroxide, putting it into the burette, and titrating some acid that was in the Erlenmeyer flask. So both solutions were aqueous solutions. You could have used this equation in order to solve for any of the components. In the case of your samples, solving for the molarity of the acid. I'm going to show you how to do that in a second. This only works when both solutions, both materials that you're mixing together, both the titrant, which is almost always going to be a solution, aqueous solution, but even your sample. So if you were titrating a solid like you did on the KHP, you could not use this equation. So it has molarity times volume over F. What's that F? Well, the F is the coefficient from the balanced chemical equation. I'm going to show you how that works in a second. So here's somebody doing titration. They missed a little bit. Look at that pink. That's a little too intense. Okay, well, at least he has a cool probe in there, so I guess that's bonus. Okay, let's see what he did. Example number 3. What is the concentration of an acetic acid solution if it takes 35.6 milliliters of a 0.13 molar solution of barium hydroxide to titrate 50 milliliters of acetic acid? So asking if I use this amount of my base and I know the concentration of my base, what would be the concentration of my acid? So I have the volume of my acid, 50 mils. I have the volume of my base, 35.6 mils. And I have the concentration of my base, 0.13 molar. What I don't have is my molarity of my acid. That's what I'm solving for. So if I take the dilution equation, MV over F equals MV over F, and I need to have the coefficients. So I need a balanced chemical equation. Where this is different than the previous examples, a reaction is taking place. So I need a balanced chemical equation. So here it is. Acetic acid takes 2 acetic acids for every 1 barium hydroxide in order to make barium acetate and waters. So I need to have 2 to 1. So my coefficient for my acid is 2, and my coefficient for my base is 1. So my F's are 2 and 1. So if I go ahead and solve, and again, what I'm trying to solve for here is the molarity of my acid. It's the question asks for what is the concentration of the acetic acid. I'm going to divide both sides by VA and multiply both sides by FA. And ultimately, I get this whole mess, 5 variables in an equation. But I plug all my numbers in. 0.13 molar is the concentration of my base. The volume of my base was 35.6. The coefficient for my acid was a 2, and my volume of my acid was 50 mils, and my coefficient for my base was 1. I do that math, and I get 0.19 molar as being the concentration of my acetic acid solution. So next time we get together, next time I make one of these videos, we're going to talk about chapter 10, that one last section that's part of the third unit, aqueous stoichiometry. It's going to be about different concentration units other than molarity. We're going to look at percent by mass, ppm and ppb, they all go together because they're all units per mass. And then we're going to look at molality. Molality sounds a lot like molarity, and it is pretty similar, but has some very, very special differences. And then finally, mole fraction. And ultimately, by the end of the next video, you should be able to interrelate all 4 variables, all 4 units of concentration: percent by mass, molality, molarity, and mole fraction. Have one of the 4, should be able to solve for all of them. So I look forward to helping you guys out with the next video. Stay safe, wash your hands, avoid social contact, all that good stuff. But always remember, never forget, sig figs matter. See ya.